Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Nothing in particular. One disclaimer that I have is, even though today's talk is titled Dynamic PDP versus Dynamic POR, unfortunately, I don't have a coherent set of slides. So what I am going to do is the following. Using a first set of slides, I'm going to talk about dynamic provable data possession. So one way of achieving cloud storage integrity. And using a different set of slides, I'm going to talk about the dynamic proofs of retrievability. And then when we switch to the third part, I'm going to talk about some of the newest results, but without slides. So I apologize for any inconvenience. So let's start talking about dynamic provable data possession. Now, what is it exactly? So consider secure cloud storage. So forget about the rest of these slides. I'm going to only focus on the storage. What's this outsourced storage setting? We have a client and a storage server, and we have some files the client wants to outsource. So the client is going to send these to the server is going to store it on behalf of the client. One of the security properties we want is integrity. So if the server modifies, let's say, some of these files, can we detect it? Or if the server removes some of these files, can we detect it? So that's the integrity problem we need to address. Another security problem is confidentiality. Can the server understand the contents of these files? Maybe obtain some meaningful information to use elsewhere. So those are, in general, the two main problems associated with outsourcing our storage to an untrusted server. So that's the scenario. Now, to address confidentiality, what we can do is we can encrypt these files, keep the key at the client, send the ciphertext to the server stores them, and this encryption prevents the server from obtaining any meaningful data. So for the confidentiality part, we already can use existing standard cryptographic solutions. Now, what's the interesting part here? For the integrity, again, there are standard solutions that exist. For example, I can hash the file before outsourcing, obtain some digest, keep this digest locally, again send the file to the server, and then at some later point, if I want to verify the integrity of this file, what I can do is I can ask the server to send me back the file. Once I receive it, I hash it back, compare the output with the digest I was holding. Make sense? This is a very standard approach for checking the integrity. Alternatively, I can, instead of a hash, I can use a MAC, keep the key locally. Now, the advantage here is that in the hash-based solution, I may need to keep one hash per file, whereas here, I can keep one key for all the files that I am going to outsource, or I can do the asymmetric version and I can sign them and maybe send the signatures to the server as well. And later on, I can request, give me back the file together with its signature or MAC, and I have no idea what happened. So then, once the server sends me back the file together with its MAC or signature, I can again run the verification, and if it accepts, now I know the file integrity is protected. Now, what's the problem in these standard approaches? The client only stores a single key for, let's say, lots of files. There's no problem there. The client storage is very low. The server storage, it's the file associate and let's say an associated signature or MAC. That's acceptable. I mean, if I have a 1 GB file and then let's say a few hundred bits extra for the MAC or the signature, that's still okay. The problem is the communication. If to check the integrity, I need to receive the files from the storage, then that's not possible realistically. So that's a very inefficient operation. If I am storing 10 GB data, actually my current Dropbox account stores more than 20 GB. So if I need to retrieve all that data to check the integrity, then that's very costly. So the whole problem we are trying to solve in both dynamic provable data possession and dynamic proofs of retrievability type of works is to be able to verify this integrity with very, very small communication and computation. That's the whole goal. Now, as I said, there were these seemingly two different approaches. PDP type of approaches, POR type of approaches. So let's first see them independently, and at the end we are going to talk about the relationship between them. So for efficient solutions, the first work is by Ateniez et al. In 2007, provable data possession. The idea is the following. We consider a file split into blocks. We have a key, and using that key, we create a tag per block. So for each block, we create a tag. Now, when we outsource the file, we also outsource these tags, and the server stores the blocks together with the tags. At some later point, when we want to verify the integrity, the client sends a challenge. This challenge, in some sense, picks random blocks. So let's say 1, 4, and 7. Now, the server creates a combined tag out of tag 1, tag 4, and tag 7, creates one tag. So out of, let's say, multiple tags, it creates one tag. Similarly, from multiple blocks, it creates one single block, and then sends these back to the client. So for communication, the only thing that's sent back is one combined block, one combined tag. And
there are two steps here, right? So you could also do the same thing as just send back 3 blocks. Would also kind of improve it. And then there's the way of combining these 3 blocks into one, right?
Very good point. So you are saying, for example, what if all these 3, 1, 4, and 7 were sent separately? That would still be better than sending the whole file. But we can even improve it to O1 communication, essentially. Constant communication by combining them in a clever way. And this combination can be verified against this key. And of course, we know what we challenged. So this verification procedure can run. If it accepts, we are confident with high probability that the file is kept stored intact. Now, what's the problem here? The problem is that if, let's say, I want to change one of the blocks here. So I want to change some of the blocks. What needs to happen is that now the server has essentially 2 copies, the old version and the new version. And when I challenge, there is no way to understand whether the response was based on the old version or the new version, because both versions have valid tags. So that's the main problem. If I update the data, both versions will have valid tags, and therefore there is no way for the client to verify whether the old version is used or the new version is used. Now, to make it dynamic, we are going to require a data structure. We can use a Merkle tree, or as Irway et al. Described, we can use a rank-based authenticated skip list. What does it mean? First of all, rank-based means the following. At each node of this skip list is a tree-like structure, a binary tree-like structure. Each node contains how many blocks, how many leaf-level nodes can be reached from that node. So there are 7 blocks in total. From root, I can reach 7 of those. Here, I can reach 2 of those. So I can reach this one, or I can go right and reach this one. So I can only reach 2 blocks. From this node, let's say, I can reach 3 blocks. Which 3? 4, 5, and 6. So those are the ranks of the blocks. So now if I want to search in a rank-based structure, how do I do it? Let's search for 5. So I start at the root as usual. Now when I look at the root says if I go down I can reach, I can reach 7 blocks from the root. If I go down I can reach 6 of those. If I go right I can reach 1 of those. Now I am looking for 5. 5 is less than 6. Okay? Which means I should go down. So what I did here was, if I go down, I can reach the first 6 blocks. I'm searching for the 5th block. It is within those first 6 blocks, so I should go down. Now what should I do actually? So if I go down, I can reach 2 blocks. Which block I am searching? 5.
So it's not really the block number, it's a block ID, right?
No, it's the number of blocks that are reachable. So for example,
5 is the block ID.
5 is the block ID.
The 5th block.
The 5th block, this one.
No,
I
it
am
just
trying.
happens there to be, but it's
No,
not
it is
the-
consecutive here. So for rank-based data structures, the block numbers are consecutive. So starting from, let's say, 1 or 0, whatever your consensus is, and then incremental.
So why not use the bind?
I will get to it. Just let me finish this search, I will answer that. So now, if I go down, I can only reach 2 blocks, whereas I am looking for block 5, which means I shouldn't go down. So now I go right, okay? Now the moment I go right, remember, I skipped over 2 blocks. So I need to change what I am searching for. I was searching for 5, but I skipped over 2 blocks. So I now need to search for 3 in the remaining part of this data structure. Now what should I do? So if I go down, how many blocks can I reach? 1. Which block I am searching for now? 3, right? No longer 5, it's just 3. Since 3 is greater than 1, I need to go right again. When I go right, I am skipping over 1 block, so I need to now search for 3 minus 1, that's 2. Now, again, if I go down, how many blocks can I reach? 2. It says 2 here. So, which block I am looking for? Number 2, which means now I can go down. So I go down. Now, since I went down, I didn't change the block I am searching for. I am not skipping over anything. So I still continue searching for 2. Now, if I go down, this is a leaf node, which means there is 1 block there. But I am searching for 2. This means I need to go 1 more right. And now I skipped over 1 block, so I am searching for 2 minus 1, which is index 1. I am here. If I go down, I see 1 block. Should I go down? Yes, because I am searching for 1. Done. Any questions about this rank-based property here?
Maybe only why it's useful with it, but that's...
Yes, that ties to Olia's question as well. Now consider any other, let's say, type of data structure where these blocks have explicit indices. Meaning, for example, as Ole was suggesting, let's say this is block index 1, this is 5, 10, 25, 50, etc. So not necessarily consecutive and not based on actual order of the blocks. Now, there are 2 main problems. One is that whenever I try to insert some new block in between, now all the block indices must change to the right of that block. So that's a very big problem. Now suddenly the insertion in between becomes actually a linear time operation. Same for deletion. If I try to delete, let's say, block number 4 here, now I need to call this 4, this 5, this 6. So I need to essentially shift all these indices. Again, a linear time operation. What can happen here is that the moment, let's say, I remove block 5, I also remove this one, okay? Now this rank becomes 1, this rank becomes 2, 3, 5, and 6. Okay, so all the ranks up to the root were decremented by 1. That's it. I don't need to change anything else in the data structure. So with only logarithmic effort, now I can do these shifts because these indices are not explicit. They are implicit from the ranks. So the next time I search for index 5, this one was removed, remember, it will find this block, which is the new 5th block. Make sense? Now, what does authenticated mean? Most of you already know this. The value, let's say, the hash value stored at this yellow block is computed using the hash values of its children, the green ones. So that's true for any node in the structure. For example, for this yellow node, the hash values of the green ones are used to compute the hash value of the yellow node. Which means each node depends on its children. So if I change any node within this structure, all its ancestors need to be changed. And because we are going to use a collision-resistant hash function, this means if anything changes within this structure, the root value must change. So if someone changes the file, it will be detected because the root value will be changed. That's the authenticated structure. So this hash of this root we call the digest or the metadata. Now what the client will do is it will keep this digest locally. It's going to send the blocks with their PDP type of tags together with this data structure to the server. Alternatively, the server can construct the same structure if they agree on some random seeds because it's a randomized data structure. But in any case, now the server stores this authenticated rank-based skip list as well. Now, when we challenge, let's say 1 and 3, again random blocks, something similar to PDP will be done. So the server will combine these blocks to obtain a single block. There is no need to combine the tags. It will only copy the first and third tag to the proof. And then to verify first and third tags, remember what we said. Each node depends on its children. So consider the path from this node up to the root. We have this parent. It has 2 children, this one and this one. This orange one's hash value need to be included in the proof. So it is one of the children missing along the path to the root. For the third one, we go here, this children is missing. We can combine these, and then this children is missing. So the proof.
But the leaves, you have the tags, you hash the tags.
Yes. So the proof is this actually. The combined block, the tags that were challenged, and then the missing parts of the data structure for us to be able to recompute the root value. When the client receives this proof, first of all, we will do the PDP verification of the block and the tags. Now, if it verifies, now we are going to do the rank-based authenticated skip list verification. So we will start with this empty structure. We will start computing hashes. So here, this is, as you said, the hash of the tag. Now I can combine these 2 hashes to get the hash of this. And I can also combine their ranks. Then I can do the hash of this. I can combine these two to get the hash of this, and the rank will be 4 here. I can combine this and this to obtain the rank 6 and the hash value here. Finally, I can combine this hash and their ranks to obtain the root. Now I have obtained both a rank for the root and the digest value for the root. The ranks tell me which blocks are these tags for. So through these ranks, I can easily compute this is the first tag, this is the third tag. And then with the hash of the root, I was storing that digest, so I compare if it is the same as the one I was storing. Any questions here? This is basically how the dynamic provable data possession works. So if I want to modify, let's say, the fifth block, I send a new block together with a new tag. Now, this modification, remember, the block will be changed, the tag will be changed, and then the path to the root will be changed. So there will be new hashes and new rank values possibly. In this case, the rank values don't change because the number of blocks stay the same, but possibly they change. The server sends the orange things that are necessary for verifying, for reconstructing these. So what will be sent is the old proof for the fifth block that I changed. So first I verify this old proof using the same strategy, and then at the end it should be the same as the old digest value I have. Then I know what the new tag looks like. I put it here instead of the fifth block, and then I recompute again. Now I obtain a different digest because this is a modification operation. So now I just update my digest with this new one.
So this is so that the client doesn't have to store the whole tree only the root.
Exactly. So all these proofs, these verifications, etc., are logarithmic time with high probability. We say with high probability because skip lists are randomized data structures. So their worst case is not logarithmic, but they are logarithmic with high probability. I mean, in terms of the height. Some very quick notes about this. Some further work that can be done or that has already been done. Now, distributing this to multiple servers was a challenge, or replicating the data with multiple servers, without, of course, increasing the complexity. Now, for resiliency against failures, this will be more clear in this POR type of line of work, but essentially proofs of retrievability use erasure codes. So error correcting codes or erasure codes. So that even if some part of the data is modified or deleted, we can still recover the original. Now, another thing is, in all these works, they don't talk about what happens if the proof fails. So the server sends this proof, the client verifies, and it's rejected. What should the client do then? We have developed some actually official arbitration mechanisms. So both the client and the server can go talk to a judge, to an official, let's say, court, and we can prove which one is actually doing it right. Is the client trying to blame the server, or did the server actually corrupt the data? There are works that are called public verifiability. It does not cover official arbitration, because in public verifiability works, a client can actually produce some fake, let's say, values for verification, such that it can blame an honest server. So public verifiability does not do the job for official arbitration. Some of the important works in this area for static provable data possession and proofs of retrievability, the two very important works are the Ataniese et al. Provable data possession work and Shaham and Waters compact proofs of retrievability. Shaham and Waters have a journal version That's much better actually. I recommend reading that one. For dynamic provable data position, we have this Irvay et al. Work. That's the first in 2009. Then we created a distributed and replicated version of this, where the client does not have to be aware of how many servers are used, and the client's, let's say, workload is independent of the number of servers employed. Later on, we have created some optimizations. Mainly, the optimization of a flex list or flex DPDP is that now one problem with a rank-based structure is it assumes all the block sizes are constant. They are the same. Now, in practice, if I want to modify a file, my modification may not be an exact block size. And in those cases, the existing DPDP types of works have some problems. In the flex DPDP, the idea is that instead of indexing block numbers, we can index, let's say, byte indices. So now any number of bytes can be inserted anywhere. The blocks can have different number of bytes and so on. For dynamic proofs of retrievability, which is the next part of this talk, I will change the set of slides. The first one was by Cash et al. In 2013. This uses oblivious RAM as the underlying structure. Later on, Shi et al. And Chandran et al., they constructed more efficient schemes, realizing that a full oblivious RAM is not necessary. It will be very clear in the next talk. And this is the surprise result. This is currently under submission. We know now how to create dynamic proofs of retrievability using only dynamic provable data position and static provable data position. So in essence, even though dynamic POR was first invented in 2013, with this new result, in 2009, we could have already had dynamic POR.
And the 2009 scheme is what you presented before is the scheme?
Yes, that's the Irvay et al. Scheme presented in this construction. And finally, for the official arbitration, we have a publication on how to do it properly such that showing public verifiability is not enough, and how to do it such that an official court can actually decide which party is the right one. I'm going to switch to the next talk, so if there are any questions, I can answer now about this, or I can switch to the dynamic POR works.
You could also do diffs instead of kind of replacing blocks. You could also just have like SVN does it, or like you just.
So exactly, that's actually what we realized in this flex list, flex DPDP line of work. Those diffs are not constant size. So we needed to modify the rank-based structure. Instead of ranks, now we have lengths of blocks. So essentially, each node specifies how many bytes you can reach from that node. And once that's done that way, we can easily handle variable length blocks. One interesting result we have there is we have implemented this flex DPDP, and we also implemented static PDP. PDP is currently the most efficient known construction for the static case. We implemented both. We tried using, for example, Planet Lab. We tried both locally and on Planet Lab on the internet. What we realized was the following. If you implement static PDP, as it was described in the original Athenias et al. Paper, in terms of the server workload, it's worse than flex DPDP. It's actually worse than the dynamic case. Now what you can do is, you can modify the PDP structure slightly such that the exponentiations that are the hardest workload, you outsource the exponentiations to the client. So the server doesn't perform exponentiations, the client does them. And this increases communication bandwidth, but decreases the server load. Then it can be faster than the dynamic version, but even in those cases, as far as the client is concerned, so the time you send the challenge until you get back it and verify it, there was actually no noticeable difference between the static PDP and flexible dynamic provable data possession. So that's a very interesting result. In practice, we can use flex DPDP almost as efficient as its static version. So the other thing, as I promised, is now the dynamic proofs of retrievability scenario. So what's the difference? As I said, now we are going to employ erasure codes. This work is initially presented by David in Eurocrypt 2013. Later on, Daniel modified some of these slides. Finally, I modified some of them, but mainly it's their slides. Now, these parts we already know, so I am going to skip. So, the idea is the following. Let me skip those. The proofs of retrievability. The first work on this was by Jules and Kaliski. But as I said, the suggested work is by Shaham and Waters. Now, what happens is that the guarantee a proof of retrievability work tries to provide is that once the challenge is verified, it should mean that the server must know all of the client data. Now, what does it mean to know all of the client data? We know actually how to formulate those type of things in zero knowledge proofs of knowledge. What do we do there?
Show that there exists an algorithm that outputs it.
So we have an extractor algorithm that can extract that data by possibly rewinding, maybe asking multiple questions and so on. So we do the same idea here. Now, what we know is that essentially we want logarithmic or polylogarithmic complexity, and this is known to be optimal in terms of online memory checking works. There are lower bounds proven there. And this is the optimal also known in this provable data possession world. Now, the original, let's say, POR type of scheme, the static version, roughly works as follows. So we have the original data at the client. The client first encodes this data through an erasure code. Now the data gets larger. Now what this erasure code enables us is, let's say, it depends of course on the parameter of the code, but let's say even if half of this encoded data is deleted, and it needs to be of course random deletions, even if half of this data is randomly deleted, we can still recover all of the original data. That's what the erasure code buys us. It increases the storage size, but then it lets us to be able to recover the whole original data even if we have some loss. The, of course, stupidest way would be to duplicate the same data twice. So even if the first half is removed, I still have one copy of the data. But of course, this is not random erasure. Erasure codes protect against random erasures. Now, once we encode this similar to a PDP type of tag, we create these tags, let's say with a MAC or a signature, to be able to verify the integrity of each one of these blocks individually. So we first encode the data, and then for each encoded block, we create a tag to be able to verify the integrity of that block. Now for auditing, for challenging, again as usual, we pick a random set of blocks. And then for these, the server, the server sends us something similar to the PDP. So it can somehow, let's say, combine these blocks and the associated tags, and then we. Now what this tells us is the following. So these are 1/2s, I will talk about it. Is there a? There's none. Okay. So if, let's assume. I can? Sure. So assume that the server knows less than half of these encoded blocks. Okay? So this is the encoded data. And let's say out of these blocks, some of them the server corrupted or erased. Some others remain. So if the server only has less than half of these encoded blocks now as the original ones. Now the issue is that we are challenging randomly, and the probability that we don't hit any of the erased blocks in that case will be 1 minus 1 over 2 to the security parameter. So if we challenge, let's say, 80 blocks, the probability that we don't hit a changed block will be 1 over 2 to the 80, and the probability that we will detect a problem is 1 minus that. Make sense? So if the server removed a large portion of these, large meaning something that we cannot recover using the erasure code, then we detect it with very, very high probabilities. Now, consider the other way around. Let's say the server still has more than half of these blocks. So the server has most of them. Now, even if I don't catch that the server deleted some of these blocks, I don't care, because the erasure code will enable me to recover back my original data. So that's the high-level idea of a POR scheme. If the server has less than what the erasure code can recover, I will detect it. If the server has more than what the erasure code can recover, even if I don't detect it, I can still recover my original data. So the original constructions were static. And the reason that's static is I will explain in just a second. Now, why is it difficult to make these constructions dynamic? So first of all, because of the erasure codes, if I update, let's say, 1 bit of this original data M, it will change linear number of keywords in the encoded data. So this erasure code is very bad in terms of efficiency of the updates. If I change something very small in the original data, lots of things need to change in the encoded data. Now, think of the other way around. Let's consider encoding blocks of data individually. So I only encode this chunk here. This chunk is encoded here and so on. Which means if I change one of these chunks, the change will not propagate to other chunks in the encoded data. Now, one problem is that, so that's good for efficiency, but the security problem here is the following. Now, remember, to lose actual data, the server now needs to erase or modify more than half of the corresponding erasure coded data. The main problem is the following. Remember how we were challenging. We were challenging randomly. Now, the more than half of this particular encoded data is actually constant size. So as compared to the whole data size, it's constant. Which means I have a very, very low probability of hitting one of these. To make that probability high, then I need to challenge each one of these code blocks, let's say, individually. But then this makes the challenge complexity linear. So if I keep my challenge complexity constant, then my probability of catching will be very low. To keep that probability high, then I need to go to linear complexity. So what we want, as we said, is polylogarithmic. Now I can try to hide this association between these individually encoded blocks by permuting them. So the client knows a pseudorandom permutation, let's say. So first we encode each block individually and then permute those so that it's hard for the server to erase a particular block without erasing many blocks in the total. So if the server does not know which blocks are the blue ones, his attack is now much worse. But the moment we switch to a dynamic setting, let's say I am going to update, let's say, one of these blue blocks. It is going to affect this blue code word, which in turn I will have to say to the server, update these locations. The moment I tell the server to update these particular locations, now he knows all these locations are tied together for the blue, let's say, code word. Now he can erase those. So update of the data gives a lot of information to the server to perform the same attack as we discussed. If I try to hide it, I need to update a much larger data so that not only the blue blocks, but maybe I also re-encrypt some of these other blocks and perform unnecessary updates. But then now the update gets inefficient. So in all these approaches, either it's inefficient or insecure. That's the main problem that it took us, let's say, 4 years after the dynamic PDP to create a dynamic POR. These erasure codes were the main problem. So our main idea was to use oblivious RAM. Why? Oblivious RAM hides the association between the client request of the update, so I want to update a particular block, and what the server does. So the server updates that location, but without knowing which location it updated. So by hiding this access pattern, what we can do is, so get this data, encode each block individually, and then put this after a permutation, although the ORAM construction already performed the permutation, so we don't need to explicitly do it, and then store it in an ORAM structure. For reading or writing to a particular location, for example, to read this location, I need to read the whole code word and then decode it. So I send read requests for each one of these through oblivious RAM. But remember, these sizes are constant, so efficiency is not a problem. So I do constant number of oblivious RAM reads. For writing the same, I need to first get it, modify it, re-encode, and then write those locations. But again, each time, one part of data is associated with a constant number of encoded, let's say, blocks. So always constant number of oblivious RAM reads and writes. Again, for audit, I am going to check, let's say, security parameter number of random locations. And we require ORAM to provide us authenticity. So for reads, we require the ORAM to provide us also to essentially the same thing as PDP tags, to be able to verify that what we read was indeed the correct value. And we can achieve these again through, for example, other mechanisms through max and so on. So for each one, we do a random read here, and then if all those reads verify, essentially if all the tags match in some sense, then we know we achieved it.
So why do you have to use ORAM?
For audits?
Yeah.
For audits, you don't need to actually. Because it is random locations, it doesn't tell the server anything. I will actually get to some of the newer results after this. Maybe we can talk more about them in detail. And again, the intuition for this security is the following. So let's say we have an adversary who can answer these audits with non-negligible probability. Now we want to be able to extract the whole data from this adversary. So what we are going to do is, as usual, our extractor will keep rewinding and auditing at different random locations. So at each rewind, we will audit at different random locations. Now, if the audit is successful, which happens with non-negligible probability by our assumption, now we are going to fill the code words in our empty structure. So we start with an empty, let's say, file. We start filling in locations each time we receive a verifying response. We rewind again, ask, fill in more locations. Now, what we prove in the paper is that the expected number of filled-in locations here will be large. It will be enough for us to essentially decode back the original data. And because of the obliviousness of the ORAM structure, because the server has no idea which parts we are reading, then this tells us these locations will be distributed randomly throughout the file, throughout the encoded file. Now what this tells us is that with very good probability, for each one of these individual code words, we will have more than half of the code word filled in. So if we have a large fraction of the whole encoded data that is randomly distributed, then for each particular code word, with high probability, we will have more than half of the blocks already filled in. If we have more than half of the blocks for an encoded thing, we can decode back to the original. Again, these half, etc., these depend on the erasure code you use, but you can tune the parameters as you wish. Computer science people love 2, right? So 1/2 to the something is our favorite. That's the reason we use these numbers. Now, one, of course, issue is that the standard oblivious RAM security does not include rewinds. So standard POR or PDP definitions include rewinds. Standard zero knowledge proofs of knowledge, the extractor there can rewind. But standard oblivious RAM definitions don't allow rewinds of the adversary. So there we needed to create a modified new definition. We called it next read pattern hiding to define what type of oblivious RAM we want. So that's the new definition we provide. It's essentially the oblivious RAM definition, but it allows rewinds. And we showed that actually some of the already existing oblivious RAMs already satisfy this definition. So it's not a completely unrealistic definition. Even though it wasn't shown before, these previous schemes already achieve this definition. Now this was the first.
What's the definition?
So think about the standard oblivious RAM definition. So let me talk about these offline and use the board. Let me finish this. We are almost at the end and we can talk about more details. But the main idea is the following. We are going to perform oblivious RAM reads to fill in these locations, right? So we are trying to hide the access pattern of these reads. So we perform reads and we want the adversary not to be able to distinguish different sequences of reads. And we want this to hold even for the cases where we keep rewinding the adversary.
I thought that you mostly want to hide writes when you do updates, no?
I will get to that as well. Very good, let's say, observation. Now, these I am going to skip because this no longer matters much. There are more efficient constructions. So one open problem we had in this paper was is the use of oblivious RAM inherent in this dynamic POR type of solutions? So do we need these oblivious reads, oblivious writes, etc.? It turns out in Chandran et al. And Shi et al. Constructions, we don't need a full oblivious RAM. Now, what using oblivious RAM buys us in dynamic POR is the following. If I use oblivious RAM within dynamic POR, even the access pattern of the client is hidden from the adversary. So the server has no idea what the client is doing. Where is he reading, where is he writing, etc. So this is an additional benefit in a dynamic POR scheme. But the original dynamic POR definition does not capture this. It doesn't require the dynamic POR to hide the access pattern. So if you don't want to hide the access pattern, it turns out you still need some obliviousness for security, but not a full ORAM construction. So I will going to briefly discuss this after this talk. So this is a very interesting point. We tried to prove an impossibility result. It turns out it's not impossible. Now, so what we know for dynamic PDP is there is nothing secret at the client side. Essentially, in the dynamic PDP construction, there is a public key that the client keeps and a digest value. So those values can be revealed. The client does not need to hide those. Public key is for the tags, and essentially it's the definition of an RSA group. That's it. One small but important difference between original static PDP tags and the dynamic PDP tags is that static PDP relies on the RSA assumption. Dynamic PDP only relies on the factoring assumption. So the tags are simpler in their case because this data structure on top takes care of other things, so the tags can be simpler.
But you can think of it as a signature scheme that's habitually verifiable, or
you can think of it that way. Now, for dynamic PDP, we know how to do this without any secret state at the client, but ORAM inherently requires a secret state at the client. So for the dynamic POR constructions today, we don't know how to do them without any secret keys. So that's still an open problem. And yet another open problem, we talked about this next read pattern hiding security we defined. Does it have other applications? Any questions about this, except the ones, the newer results, etc., that I will talk soon?
And
okay.
The impossibility of the impossibility besides.
Okay, so then let me stop the recording here, and then we can talk about it on the board in more detail.